All right, let's dive into something pretty wild. We're going to look at a scientific paper that talks about engineering light in a way that feels like it's bending the rules of time. But just to be clear, this isn't science fiction. It's a really clever fusion of advanced optics and, believe it or not, living biology. And this concept, it could seriously change how we think about everything from creating biofuels to developing targeted medicine.
So let me just start with the central kind of mind-bending question here. Can a pulse of light actually get to its destination early? I mean, can the peak of a light wave show up at the finish line before it even seems to have left the starting block? It sounds impossible, right? Well, the answer, amazingly, is yes, but it's probably not in the way you're thinking.
And this is the absolute key. We are not breaking the laws of physics. No warp drives today. What we're actually talking about is a really cool phenomenon called negative group delay. Think of it as a clever trick of pulse reshaping. If you have a long wave, you can cleverly change its shape as it travels, which makes the peak of the wave show up at the end, seemingly before the original peak even started its journey. But the actual information, the very front of that wave, it never ever breaks the speed of light. So to really get our heads around this, here's how we're going to break it down. We'll start with the core of the device, what the paper calls the prism and the maze. Then we'll get to the most surprising part, the living component. After that, we'll see how we can put this light to work, and finally, we'll look at the plan to turn all this from a cool idea into a reality. Okay, so how on earth do you build a device that can reshape light in such a specific and kind of weird way? Well, the paper proposes this brilliant two-stage setup. You can really just think of it as an incredibly precise sorting system for light itself. So in step one, you've got a prism-like part that takes a pulse of light and just separates it out into all its different colors, just like a rainbow. Then comes step two, where those colors are sent into a microscopic maze. And this is where it gets really smart. The maze is designed so that some paths are shortcuts, and that's what creates the negative delay. At the same time, other paths are long detours that create a normal positive delay. And it's all happening on the exact same chip. Okay, so we've got a prism and a maze. That's pretty standard for an advanced optics project. But this is where the whole thing just takes a wild turn. The researchers want to integrate a living biological component right into that maze, a specially engineered microbiome, or what's called a biofilm. But why? Why would you ever want to add living stuff to a high-precision optical device? Well, this chart explains it perfectly. It's all about the trade-offs. A traditional solid-state device, that gives you stability and direct electronic control. It's predictable. But a living biofilm, that offers something else entirely. It's got the potential to self-repair if it gets damaged. You can tune it with chemical signals. It just opens up this whole new world of interactions that you just can't get with plain old silicon. So we have this incredible, futuristic-sounding gadget that mixes light and life. Cool. But what's it actually for? Let's check out how this tech could be put to work in two very different but equally powerful ways. So the first idea is a concept called the Light Vault Bioreactor. Just imagine for a second a radically more efficient way to grow microorganisms like algae, the stuff that's super important for biofuels, for food, and a whole bunch of other bioproducts. And we're not talking about a small improvement here. By tweaking these light pulses, the system could actually stop the microorganisms from getting damaged by too much light, which is a huge problem right now. It could time the light energy perfectly to match what the organisms need to grow. And with a clever cleaning system, it could run with over 95% uptime. That really paves the way for truly massive microorganism farms. All right, the second application sounds like it's straight out of science fiction. It's a concept for a medical device called the biophoton patch. And this is really a long-term vision for using this tech to deliver incredibly targeted therapies. The whole idea here is to use these precisely shaped light pulses to destroy specific cells, like cancer cells, while leaving all the healthy tissue around them completely unharmed. The targets they've set are incredibly ambitious. Destroy up to 90% of the targeted cells while only raising the temperature of the healthy skin by 6 degrees Celsius or less. Now, it's super important to note, the paper is very clear that this is a long-term concept. It's not something that's anywhere near ready for clinical trials. So you've got these incredible world-changing ideas, but how do you actually get from a concept on paper to a working prototype? Well, the white paper lays out a very clear, very methodical roadmap to test the core ideas. And this is what I love. It's not just wishful thinking. They've got a structured 60 to 90-day plan just to see if it's feasible. It starts with building the parts. Then they'll do optical tests to actually measure the pulse delays. After that, they'll run control tests to prove the biofilm is actually having an effect. And finally, they'll stress test the whole system to see how tough it is. And for that first big test, here's what it all comes down to. The key measure of success is showing a negative group delay of around -5 to -15 picoseconds. That is just an unbelievably tiny slice of time, 15 trillionths of a second. If they can achieve that specific, measurable goal, that would prove the fundamental principle actually works.
And you know what's even better? The researchers have already thought through what could go wrong. This just shows how rigorous the project is. They've got a risk register. Like, what if people misinterpret the results and think it's faster than light travel? They have a plan for that. What if the biofilm gets damaged by the light? They have strategies for that too. This is just careful, responsible science in action.
In fact, they state it so clearly in the paper's ethics section, and I think it's really worth repeating. No superluminal communication is claimed. All tests include front velocity verification. They're basically putting it out there in black and white to avoid any sensationalism and stick to the real, verifiable physics.
So, at the end of all this, we're left with this one big thought. This research is so much more than just a clever trick with light. It's really a glimpse into a future where we merge the digital precision of optics with the adaptive, self-repairing power of biology. And it really makes you wonder, right? What other incredible possibilities are going to open up when we truly start engineering with both light and life?